Okay, this is our lecture 6. So I'll start by introducing the negative binomial distribution to start with, but just as an announcement that I think probably in the middle of this lecture or towards the end of the lecture, I will talk about the QQ plot. I think some of you had questions about that in the homework. It's about how good a QQ plot is considered to be good enough. So I'll give you some examples to have some visual understanding. Okay, so first let's revisit the negative binomial distribution. So last time we said that negative binomial distribution is a count distribution. It has one more parameter than the Poisson distribution does. So Poisson only has one parameter, which is both the mean and the variance. And this is a very strong constraint for Poisson distribution. Well, negative binomial allows us to make the variance bigger than the mean by introducing the dispersion parameter. So there are two ways to motivate the negative binomial distribution. We use the Gamma-Poisson hierarchical model, this motivation. So what it means is that we assume the Poisson parameter itself to be a random variable that follows gamma distribution. So this additional layer of randomness allows xi to have bigger variance than the Poisson does. So essentially, there are two formulas I would like to introduce to you, which is very important results from our probability. So the first result, so let me simplify our notation a little bit by dropping those sub-indices. So the first one is that, let's say I have x given lambda follows Poisson lambda, okay? And then lambda itself follows gamma alpha beta. Okay, so one important formula is about the expectation given the conditioning, which is often called the Tower rule. So what this says is that we can write the expectation of x without conditioning on lambda. So this is what we call the marginal distribution. So how do we understand the marginal distribution? It is that for the marginal distribution, we can actually, by using the joint distribution of x and lambda, taking that joint probability density. So probably we can write it down. So it's like the probability, I'll write it here. The probability that x, let's say the Poissons, we take count values, taking the count lowercase x, this probability can be calculated as the integration of this joint probability that x takes value x, while lambda takes its own value lambda. And we take the integration of lambda. So this means that by doing this integration, we can remove one random variable from its joint density and only keep the x. So what does this mean? This means that in this joint density, we have two random variables, each take a value. But since the value of lambda can change and it's not necessarily affecting the value of x, so then what we do is that we basically take the summation over possible values of lambda. And because lambda is continuous, when it's a continuous summation, it becomes integration. That's the most intuitive way of understanding this. So how do we go from joint probability to marginal probability? So if this is still not intuitive enough, you just think of both x and lambda being discrete. Let's say x take two values, 0 and 1. Lambda take another two values, 0 and 1. So in this case, the joint probability will have 4 probabilities for 4 combinations. But if we only look at x only, then x has only two values, 0 and 1. So what we do is that for x equals 0, we consider lambda being 0 and being 1. And we take the sum of those two joint probabilities. That will be the marginal probability of x equals 0. And the same thing applies to x equals 1. So that's the idea. So therefore, you see, to obtain this joint probability, we can use the conditioning argument. That is, this is equal to the probability of x equals x given lambda times the density of lambda, d lambda. So this is what we know from the probability as well. So conditioning times marginal gives us joint. So this conditioning probability can be from Poisson, while this can be from the gamma. So that's just to give you a rough idea of how we can go from this two-layer hierarchical model into the marginal distribution of X. And here I'm telling you that this marginal distribution is just what we call negative binomial distribution. So coming back to the power rule, this is very important for calculating expectation. It's not even, you don't even need the integration for this. That is, we can first write down the expectation of X given lambda, and then we take another layer of expectation just for lambda. So you can just know that the inner expectation is for the conditioning distribution, while the outer distribution is just for the lambda distribution. So this is what we call the Taylor rule. So you see that you can actually very naturally see what this is, right? So given that the expectation of the inner one is known to be Poisson, and we know that given lambda, this expectation is lambda. So we get the expectation of lambda. So it ultimately becomes the expectation of alpha, gamma, alpha, beta. That will be how we can calculate this expectation. So in other words, what we could do when defining the negative binomial is that we can set the alpha, beta value so that these two values can satisfy their, so based on whatever formula for this gamma. So because there are several parameterization of gamma, so I'm not going to give you a formula here, but you can just know that this is some function of alpha and gamma, alpha and beta, sorry. So you can just set this number to be equal to what you have in the data. So let's say you have n observations of X. You can calculate an average, we call X bar. And then you need to set that X bar to this F alpha beta. And then given the variance, I'm going to write that. The variance of X, this is a second important fact that this needs to be written down in two terms, but you can see it's very interesting. One is that you have the variance of the conditional expectation. And the other term is you have the expectation of the conditional variance. So you alternate what's variance, what's expectation in those two terms. And then they together will give you the marginal variance. So again, here we're going to use that the conditioning expectation and conditioning variance are both Poisson, from Poisson, so that they are equal to lambda. So we would have the variance of lambda plus the expectation of lambda. Both are then determined by gamma distribution. Again, so I will call this another function of the two parameters alpha and beta. So then you can see we can easily do something we call the method of moment estimation, which is something some of you learned from the 100B, right? So essentially the method of moments estimation is very intuitive, unlike the likelihood, maximum likelihood estimation, which you need to specify the likelihood based on probability density functions. The methods of moments just need you to replace the expectation by their sample version from your data. So you can just say, okay, I will set X bar equals to my alpha hat, beta hat to be solved as my estimate. And also I can have my sample variance. I'll just write as 1 minus this one, xi minus x bar squared, right? The sample variance formula set to this to g alpha hat, beta hat. So given those two equations, you have two unknown parameter estimates. You can solve for what's your alpha hat and what's your beta hat. So this will be a very simple way to estimate the parameters of this gamma so that you would be able to draw, so you would be able to make the marginal, so that you can estimate, I should say, this will be the way to estimate alpha and beta so that you can have the distribution fit to your data. And then you can see, how about lambda? Lambda will go away in our marginal distribution because as you see from here, once I do this integration, lambda will go away. But in this density of lambda, P lambda, you will have alpha and beta. So that's why in this marginal distribution, you are still only having two parameters, alpha and beta. And that's the distribution. That is the negative binomial distribution to be specified. So to summarize, what I want to say is that given this hierarchical model formulation, you will be able to have the marginal distribution of X still as a count distribution whose values are non-negative integers. And this distribution will be specified by two parameters, which I specify as alpha and beta here. And you can correspondingly find, okay, the estimates of alpha and beta using the methods of the moment I gave you here. But moreover, given what I said, you can also, if you are able to do this integration by writing down this is the Poisson probability mass function, this is the gamma probability density function, you multiply them, do the integration for lambda, you will be able to get this marginal probability mass function for X, for the counts. And that's what we call negative binomial distribution. And furthermore, I want to say that another common way of seeing the negative binomial distribution is another way of parameterization, which is not based on alpha, beta. Instead, we write it based on our mean and variance of X. So in other words, so given this probability density function, and given what we have from here, the relationship, I can call this the mu, okay? And I can call this is the sigma square. Given this these two notations, you see, they have one-to-one correspondence with alpha beta because mu is a function of alpha beta, sigma square is a function of alpha beta. So we can also write the distribution as X follows negative binomial with mean mu and variance sigma square. So one common thing to know about the negative binomial distribution is that you will have the variance greater than the mean. So that's what we will have from the negative binomial distribution. Okay, unless what? Unless the case when this gamma distribution is reduced to a constant without variance. So whenever the alpha beta value satisfy that the variance of this gamma distribution is 0, which means, okay, lambda is no longer a random variable, but a constant that equals the mean. In that case, then the negative binomial reduces to Poisson. So you can consider Poisson as a special case of negative binomial distribution. Okay, that's the first way of interpreting the negative binomial distribution as this hierarchical model, which means you add a layer on top of Poisson by considering the Poisson parameter to be random. Another way you may consider for the motivation of negative binomial, actually this is something I learned first myself. So another formulation is from the coin tosses perspective. I think in many introductory probability tests, probability is taught via the coin tosses, right? For every coin you toss it, you have a binary outcome, either head or tail, 0 or 1. So, and you may also call it a success versus failure. So then, you know, for each toss, we said it's a Bernoulli distribution, right? We have a P probability for getting a 1 and 1 minus P probability for getting a 0. And if we do n independent tosses, and each toss has the same probability P for getting 1, then the total number of ones among your n tosses follows what we call binomial distribution, with the total as n and the probability as P. That's what we learned. But from that same setting, we can also have negative binomial. So in that case, you will have two parameters here. It's actually defined as the success probability is still called P. Okay, this is one parameter you need. The other parameter to get a negative binomial distribution is the number of failures. Okay, so R is the number of failures, or you can consider as number of zeros you get. So then what's the random variable in this setting or in this generation, in this data generation or probability generation? Is we define the X to be the random variable, and it is the number of tosses until we have R failures. Okay, so that become a random number, right? Because you know, for example, when you do the tosses, you may have, so let's say if R equals 3, that's a parameter. For R equals 3, for you, maybe you have 10 tosses until you have 3 failures, but another student may need just 5 tosses to see 3 failures. So that's why this X is a random variable. And then we're interested in the distribution of this X. And then you can imagine, what are the possible values of X? The minimum has to be, sorry, I said the number, my bad. The number of successes, the number of successes, not tosses, right? The number of successes until we have R failures. So in other words, when you stop, you have a total of X plus R tosses. So then what's the minimum number of successes before you see R failures? 0, right? You could just keep on tossing, and every toss is a failure. In that extreme case, you may have 0 successes before you see R failures. But some other people may have very, very large X. That means they just keep getting successes and not very few failures. So they have to wait a long time until they see R failures. So you see how this R is going to play a role in our distribution of X. The larger the R, the more likely X is going to take a large value. If R is set to 1,000, then you need to wait a long time to really get R failures. Another thing that will determine X is P, right? So if P is a very small number, that means you are very likely to get failures instead of successes, then you will not wait for very long to have R failures. So you can see the effect of both P and R on the distribution of X. So then from this perspective, the distribution of X can be derived in a more intuitive way. So let's think about it from combinatorics perspective. Let's say that we have lowercase x successes until R failures. So a special thing about negative binomial is that we know the last one must be a failure, because that's when we stop, right? Whenever we reach an R failure, there's no reason to continue tossing. So we know that this last one is a failure. And then before it, we have legs plus R minus 1 tosses. And we know that among these tosses, we have R minus 1 failures. So that's the only constraint we have here. So therefore, the probability is about among all the possibilities, how many cases will we have that among the first X plus R minus 1 tosses, we have R minus 1 failures. So then this will become that for the first X plus R minus 1, we have so many ways to choose R minus 1 failures. And then for each success, we will have probability P, and we multiply these probabilities together because each task is independent of each other. So we have how many successes? X successes. And how many failures? R failures, right? R minus 1 here, the last one here. That's the marginal distribution. And this is what we call negative binomial. And from this probability mass function, although here from the previous derivation, we didn't write down the formula, but if you're interested in trying, you will be able to see that after this seemingly complicated integration, you will get a form which can be converted to this one. There's a one-to-one relationship there. So given this form, I can simply show you what is the mean and what is the variance. So the mean can be shown as equal to P times R over 1 minus P, while the variance can be shown as P times R divided by 1 minus P squared. So given those two results, we can also see that there's a clear relationship, that is the variance is equal to the mean times 1 over 1 minus P by comparing their two formulas. And we know that since P is between 0 and 1, right? So as long as the P is not equal to 1, so we will not have a dividing 0 issue, this ratio is actually greater than 1. Okay, so if we have P between 0 and 1, then this one is actually greater than the expectation of X. So that's what we call that variance is bigger than the mean for negative binomial. And that's what we call in bioinformatics and many other fields who use negative binomial as over dispersion. Over dispersion stands for the fact that the variance is greater than the mean. Okay, and this also tells you that under which case we have variance equal to the mean. That will be when this ratio is equal to 1. And that is when P equals 0. So when P equals 0, it means that we will never have a failure, right? We will never have a failure. So then, so in that case, yeah, so that's the case when we will never have a failure. So then this is the case where we could not actually complete this setting because you will never have a failure. So this X will stay as infinity. So, right. So that's the case where the negative binomial is reduced to the Poisson. But I think probably I cannot really give you the intuition from this formulation because it doesn't make sense anymore. When P equals 0, how can you still talk about failures? So yeah, so that's what I want to say about the negative binomial distribution. So the key take-home message is that you can consider negative binomial as a generalization of Poisson, and negative binomial has an important feature, that is its variance is greater than its mean. So it can account for data which clearly has the sample variance, if you can compute it, much larger than its sample mean. Okay, so that's all I want to say about the derivation. So the next thing I'm going to show you is to show you something which I found is very interesting online. So let me pull that up. Okay. So I'm going to show you something here. And just as a preview, this is the model, this is the basic model used in DESeq 2 method, the newer DESeq, which is the standard state-of-the-art DESeq method. Not the DESeq we're going to introduce next, but this is for DESeq 2. Okay, so in DESeq 2, they use something called negative binomial regression. So in this setting, what's the response variable in the regression are counts. And they use negative binomial regression to find some association between the counts and a predictor or a feature they are interested in. So in our DESeq 2 setting, the negative counts are one gene's expression counts measurements across samples, in different samples. And what we are interested as the predictor is the condition a sample is in. So we are usually interested in comparing two conditions. Say one is the treatment, one is the control. So in this case, we will encode that condition feature as a binary predictor, 0 and 1. So each sample will receive a value 0, let's say if they are in the control condition, or 1 if they're in the treatment condition. So then the question we want to ask is, does the gene have different expression levels between the two conditions? Or does the gene have different expected expression level between the two conditions? So we can formulate this question as a negative binomial regression. And the question becomes to test in this regression model, does that condition predictor have a non-zero coefficient? So basically the null hypothesis is to test whether that coefficient is 0. That null hypothesis is the coefficient is 0. And if we reject the null hypothesis, we're going to call the gene a DE. So that's the basic idea of DESeq 2. So for negative binomial regression, if you are interested in knowing the details, this is something my other class right now is covering. It's basically part of what we call the generalized linear model. So in the generalized linear model, you will need two components. One is what we call a random structure. It means how the counts in your response are distributed as a distribution. How distributed under what distribution? So in the negative regression, binomial regression, we assume the count follows negative binomial distribution. And the second component is what we call the systematic structure, which is about how do you associate it? How do you associate the mean parameter of the distribution you assume to the predictor values? So in this case, we are trying to associate the mean of negative binomial. So each count has its own mean, and we want to associate that mean parameter to the predictor we're interested in, which is the condition. So in other words, you are going to have two layers in that, in other words, negative binomial distribution plays that is involved in that random component in the generalized linear model. So on this web page, which I'm going to post under our video recording, so it gives us a very practical example about how this works. So probably we can scroll down a little. So this is from a book. If you're interested in, it gives a lot of concrete examples for categorical data analysis. So in this example, the data are from a survey of 1,308 people in which they were asked how many homicide victims they know. The variables are risk, the number of victims are the respondents know. So, and then there's a race indicator. So which indicates the respondents being Black or white. So this is similar to our setting in which our condition is also binary. So you can consider this is our control versus experiment. And we have each sample has a count. So what this means is that this is a summary vector. Okay, it's not actually the original respondent data, but it's summarized. So what it means is that, so 119 Black people know 0 victims, 16 know 1 victims, 12 know 2 victims, 7 know 3 victims, 3 know 4 victims, 2 know 5 victims, 0 knows 6 victims. So there are no more people, there are no people who know more than 6 victims. So that's why we didn't continue. Okay, and the corresponding vector for white people, 1,070 people know 0 victims, 16 know 1 victims, 14 know 2 victims, 4 know 3 victims, and 1 person knows 6 victims. So it's a very succinct summary of the data. But if you really want to get the original vector, you need to expand it. In other words, you will have 119 zeros, 16 ones, 12 twos, 7 threes, 3 fours, and 2 fives. So you need to expand that to a long vector. That's your true response. And similarly for these people. And then the predictor, here you are encoding the 1,308 people by their race, either black or white. Then that's the data structure you will have. And then you run the regression. So as an analogy, you think of the response. This is exactly what it did, right? They are expanding the 0 to 2 by the numbers of people who observed such number of victims and expanding this as well. So in other words, you can consider this is the samples under treatment. These are the samples under control. And this is the indicator for treatment. This is for control. And then you run the regression. So what this first did is that I'm going to skip some of the details, is to run a Poisson regression. So in Poisson regression, between Poisson regression and negative binomial regression, the difference is that in Poisson regression, you're assuming the counts given the mean is distributed as Poisson. So the variance must be equal to the mean. While in negative binomial regression, you assume the counts, each count follows negative binomial distribution instead of Poisson. So you change the random structure, but you keep the systematic structure. So between the mean and the linear predictor, that relationship stays as the same. Okay, so this is in R, the GLM function allows you to run it. So basically you specify the response, the predictor, the data frame name, and you specify families Poisson, means you are running Poisson regression. And you will get a coefficient in the regression. So what you're interested is the coefficient for this race indicator here. So this is, so in this round, I think, yeah, it's just the way you specify the factor. Let's scroll back. Right, so in R, the default is that if you're going to input a categorical predictor, not a numerical predictor into regression, you specify the vector as a factor. So factor means you're telling R this is a categorical predictor. And the first level of the factor is considered to be the baseline. So the baseline is considered to be like the thing that has no effect, while the second level, the other levels are considered to be in contrast to the baseline, so their effects will be assessed. So in this case, basically, you can consider white to be the control, black to be the treatment. So therefore, the coefficient will be returned as race black. So this is telling you, okay, compare with white people, how much effect of being black will on the number of victims we know. So how do we quantify that? So this is the coefficient 1.73. Essentially, here to interpret that effect, I'm going to talk about that later, but you need to take the exponential of it as the effect. I'll explain that later, but let's put it here. So what's very interesting is that you're going to do a test on this coefficient of the predictor. And here, based on the test, you see a very small p-value. This tells you, okay, yes, this predictor indeed has an effect on my response. So translating this to our differential express gene scenario, we would call this gene a DE gene, which means if the expression value does change between the two conditions. Okay, so it seems we're good, right? The Poisson regression gives us a significant result, but it's not enough because we want to make sure whether the model fits our data well. So to check that, we need to compare what are the predicted counts, or we call expected counts or fitted counts given this model versus the counts we observe in our data. So this is what's expected under the Poisson model. So you see that for the people who have who know one victims, we observe 119 Black people, but our model predict 94.3 Black people. And then we go down for 2 victims, 16 observed, 49.2 fit, and so on, so on. So you see what's the key difference is that it seems the fitted values or expected values are more concentrated on the low counts, while the observed values are more dispersed at those larger counts. And the same phenomenon existed for the white people. You see, we still have 4 here, 4 people who know 4 victims, but our expected value is only 0.1. So this made us wonder whether we underestimated the dispersion in our data by using Poisson regression. And in fact, there is something in the package called CountReg, and there's a very useful tool, graphical tool called Rutilogram. So what it does is that it's plotting the square root of the expected counts, so expected frequency, how many people observe this count versus the square root of the observed frequency, 119 taking the square root, that will be put in the x-axis, and that will be the bar, sorry, my bad. The observed is the bar, and the red dot is the expected. So in this Rutilogram, we take the square root so that we can more, I would say, make the small counts more visible. Otherwise, you may be dragged by just large counts. So the small counts become not so obvious in the comparison. That's the primary reason. And so then you can see in this Rutilogram, what it does is that it tries to tie the bar, which is the observed frequency, to the red dot, the expected frequency. So you see they are connected at the top and let the bottom vary, whatever. So sometimes the bar may go below 0, sometimes maybe they go above 0. But whenever it's far away from 0, it indicates that our fitted model does not fit our data that well. So if it's perfect fit, then every bottom of the bar will be right at 0. So this is telling us, okay, probably the Poisson regression doesn't do a very good job. Then we continue to try the negative binomial regression. And in R, there's a function called gln.nb for fitting negative binomial. And actually the formula is the same. You put a response and tilde the predictor. You also get a summary, and still you try to estimate the effect of race being Black. And now you see, you still have a very significant p-value. So if you want to draw a binary decision, do I reject the null hypothesis that race has no effect? For both Poisson regression and negative binomial regression, your answer would both be rejection because the p-values are very small. But if we inspect the fitting using also the Rutilogram, you will see that it's actually doing a better job. Because if you look at the bottom, now you see the bottoms are closer to the horizontal 0 line, which means that you have less discrepancy between the fitted frequency and the observed frequency. So I'm just using this as a very, very high level introduction of the negative binomial regression versus Poisson regression. So you will have some intuition about what the diagnostics would look like when you compare different models. But just the reason I talk about this is because in the DESeq method, it uses this negative binomial regression to call DEGs. Okay, so any questions about this high level idea of negative binomial regression and Poisson regression as cases of generalized linear models? I'm going to switch back to my paper to give you some high level understanding of that very soon. And then another thing I want to show you is the Rutilogram. This is a manual tutorial about visualizing count regression using Rutilograms. I'm also going to post this to our video recording and also to CCLE. So for those of you who are interested, you can check it out. It's a very useful graphical tool to be used. So for example, this shows that, okay, the data is generated from Poisson, maybe I can enlarge this. Data is generated from Poisson, and you fit the data using Poisson. So there are three types of it, but let's focus on this. This is the same as what we have seen before. You are doing the hanging Rutilogram. So the top are connected and the bottom are hanging. So you see that this is for fitting the real data as Poisson, and you fit Poisson. Still, there are some discrepancy, right? But if you have the real data generated from negative binomial, but you fit it with Poisson, then the discrepancy is much larger. You have a lot of bars that goes really below or is really far away from the horizontal line. So comparing those two, you can see the visual difference. Okay, and also QQ plot. That's a question I promised I will talk about. Actually, I see there's a question in the chat box. So, okay, Helen Huang said that P equals 0, so always failure. Yes, so that's the case. Yes, exactly. So back to that, yes, when we have P equals 0, we can never have successes. But still, that cannot explain that this becomes Poisson, because you have to set R equals, actually positive infinity in that case. Otherwise, you will not have, so when P equals 0, you will never have X different from 0. So there's still some issue over there. But thank you for making the comment. So for the QQ plot here, this is the thing we're going to show you. Scrolling down. This is it. So basically, in this example, comparing these two, we are thinking this QQ plot is reasonably good, but this is totally off. Okay, so this is just to give you some visual inspection of what a good QQ plot might look like and what may not. So you need to understand that it will never be perfect, just as what we have seen here. Rolling back to this, even though the data are truly from the correct distribution, use correctly specified Poisson, you fit the data. Because of the randomness, you will never fit the data perfectly, or you will never actually have the actual distribution perfect, because your estimate for the Poisson mean parameter will never be exactly 3, unless you have a super large sample size. Otherwise, your mu hat will always have some uncertainty. So that's why you can allow for those deviations. And so whether the deviation is reasonable or not is actually something very subjective, I have to say. And another example I want to show you is our own paper, which is something I'm going to, okay, maybe I'm going to show that right now. So that's something I showed to a student at the end of our last class when I was asked about this question. Okay, so just give me 1 second. So this is from our own paper, and our message is that, so there are several methods for finding temporally differential expressed genes from single cell RNA-seq data. So that's the setting. And these are the existing methods. And our main point is that many of them cannot really produce valid p-values. So in other words, the p-values under the null hypothesis are clearly not uniform 0 to 1. So you see that this is something we consider to be totally off. And this is another method, which is kind of the state of the art, which we also think is off. And this is the only method which is close to it. So basically, our argument is that this method has p-values relatively well calibrated, but its power is relatively low. So power is another thing. And it's not related to p-value, this is another thing. So just to make it in short, you can have 2 tests to do the same job for the same null hypothesis. And both tests, you can have valid p-values, but it's possible that one test is more powerful than the other. So that's just the trade-off between type 1 error, type 2 error. So you can have type 1 error always controlled, but however, but maybe small. But this is the method we propose. So we think our p-value calibration is relatively good. So I would think this can give you some visual inspection about what is a good QQ plot, what is not. So I would say, in my opinion, this is okay, but this is not, this is not, this is not. So hopefully this is useful for your homework question one. Okay, so that's about it. And so coming back to our DE topic. Okay, so back to our DE analysis. So just as a makeup for our regression, the negative binomial regression and the Poisson regression. So what I actually mean is this. Okay, so let's say that we have just one gene, okay? And we have the genes counts in n samples. So I will just call those as Y1 to Ym. So these are counts in n samples. And I also have the condition predictor for the n samples. So for example, I can call them X1 to Xn. And these are binary, okay? Either 0 or 1, indicating their condition. So what I just introduced from that web page is we can do the Poisson regression or negative binomial regression. And these two regression model, like I said before, has a random structure which assumes that each count is independently follows a Poisson distribution with mean mu I or a negative binomial distribution with mean mu I and the common dispersion, which is assumed to be unknown. I'll put it here, phi. And then the systematic structure is going to link the mean parameters to the condition. So we would assume in these two Poisson or negative binomial distribution, where I'm going to assume log of this mu I to be equal to, I'll write some intercept alpha plus xi, the condition, binary condition, times beta. That's the model. That's what this model is about. And by running that regression function, like the GLM or GLM.NB, we're going to estimate this alpha and estimate this beta. So why are we taking this log function here? This is a concept in the generalized linear model called link function. The reason is that we know on the right-hand side, so beta is a coefficient which can be positive or negative. The intercept can also be positive or negative. So this value can take values possibly from this negative infinity to positive infinity. But if we inspect the mu I, we know the mu I as the mean parameter for Poisson or NB, it must be positive. So if I don't do any transformation, it's unreasonable to say mu I equals the right-hand side, which can be negative. But if we take log transformation on mu I, then log mu I can take negative values from negative infinity to positive infinity. So then the domain of the two sides are matched. So this is a very intuitive way of thinking that we need this link transformation, link function. So essentially, we are going to do maximum likelihood estimation for this model. And by assuming the randomness in our count is generated from Poisson or negative binomial to estimate the parameter. Then the parameter beta is what we saw in that R summary. How do we interpret its effect? Clearly, you see, based on this, right? If I change my beta to beta plus 1, how much would this mu I change? You see, the mu I is equal to exponential to the power exponential of alpha plus xi times beta, right? And if I enlarge beta by 1 unit, you see, if I change beta to beta plus 1, what happens is that mu I will be changed to the original mu I times exponential 1, right? Because the beta plus 1 will go to the exponential, and that will give us this. So in other words, the effect of beta on mu I is on the exponential scale. It's not on the original scale. So that's why we would call the effect size effect as multiplicative and exponential scale. Hopefully that makes sense. So this is how we are going to interpret the negative binomial regression. And you can see what happens when beta is 0. Beta 0 means that the condition has no effect on the response, right? So that means no matter whether my sample I is being in the control group 0 or being in the treatment group 1, I will always have the same mu I. So my count will not, the expectation of my count mu I will have nothing to do with the condition my sample is in. Okay, that's the basic idea of DESeq. I'll just stop here without going to the details. And one more thing to say is that this generalized linear model is something very important to learn if you are interested in doing methodology development in bioinformatics. The reason is that this systematic structure allows you to incorporate other batches or confounders into it. So you can easily incorporate other information to adjust for the effects of the condition on UI. Because if you believe that other factors also contribute to the differences of UI in addition to the condition, then you can put the other things as other predictors into the model. Okay, so now let's return to DESeq, the original DESeq, and see what the model it uses. So just to clarify that the DESeq, original DESeq, it does not use negative binomial regression. It uses something else. And we can see whether that is necessary or whether we see some issue with that. Okay, it didn't use MB regression. And also, this is something to see as an example that for the same purpose, you can develop tools from different perspectives. Like I said, GLM or generalized linear model is a convenient tool for solving a lot of the, I would say, statistical inference problems in bioinformatics. But you may also use some other approaches not regression-based. And also these things are kind of frequentist, right? You may also use Bayesian approaches, which we will not cover so much in this class, but that's also a large class of methods. Okay, so DESeq. So in DESeq, the consideration is this. So I'm going to use the notations in our notes. So basically we have I as the gene I, and we have sample J. And also we know the condition of sample J, okay? So the condition of sample J, we call that rho J. In other words, for every J, we will put it into this rho function and it will give me a 0 or 1 value. So rho J is binary. That's the condition mark. Okay, and something we need to consider is that each sample has its own sample size effect. Maybe you can consider that as the library size or some other effect. So sample specific effect, which is considered to be multiplicative. So therefore, in DESeq, it assumes 2 layers. So the first layer is the actual count of gene I in sample J. So that's the true count of gene I in sample J. So you may consider this true count to be the copy number of mRNAs of this gene, right? Suppose we know the truth. So this is assumed to be denoted by Rij, a count, and the authors assume this to follow a negative binomial distribution with two parameters, as we said. The mean parameter is denoted by I rho j. So two sub-indices. One is for gene I, the other is the condition. So which means that under the same condition, we have a mean parameter for the MB and dispersion. Let me see if it's a dispersion. Yeah, it's then the dispersion parameter for the condition, gene I condition rho j. So in other words, if two samples have the same condition, they will share the same mean and same dispersion, same two parameters in MD. So basically we can consider this to be the biological variation, which means that even though samples are from the same condition, the gene may still have different true counts in each sample, just due to biological variation. And then furthermore, we assume that there is a size factor, sample specific size factor, which we call Sj, that is multiplicative to the true counts. So then given this multiplication, we would assume that the sequencing experiment itself has additional randomness as a Poisson distribution. If you recall, we said that a Poisson distribution is a way to approximate the multinomial distribution, which we said in the last class. And if you imagine that all genes are sequenced together in one sample, it is a multinomial distribution for all genes. Then for each individual gene, we can approximate its count distribution by Poisson. So therefore, the actual or observed count of gene I in sample J, we call that Kij. That's the thing we can observe. Follows Poisson distribution with mean as the true count multiplied by the size factor, Sj times Rij. That's the second layer. And you can consider this to be what we call the sampling or sequencing variation. The second layer of randomness. Okay. And then what the author is ultimately interested in. So the interest of doing this modeling is to answer this question in our null hypothesis. That is, does my Qi0 equals Qi1? You want to see whether you can reject this null hypothesis. In other words, does the negative binomial mean differs between 0 condition and 1 condition, condition 0 and condition 1? That's the question you want to address. So you can see Qi rho j. So rho j can only take two values, 0, 1, right? You are interested in two parameters, Qi0 and Qi1. But you need to estimate everything to be able to do that. So that's the framework. Okay, then how do we do the parameter estimation, right? That's the thing the authors need to address to solve the problem. So it becomes a parameter fitting problem. So the authors made several assumptions for the parameter estimation. And then I'm going to talk about them one by one. So how to estimate the parameters. And if you look at the DESeq paper, you will see everything I said here, but I'm just introducing in a slightly different way by reorganizing the contents for the ease of understanding. So the first thing the authors assume is that if I have different J's for the same gene I, then what they basically assume is that they can estimate this Sj, size of sample J, by pooling genes together. Because you see this J, Sj has nothing to do with gene I. It's not specific to one gene. That is the same for all genes. So they first estimate Sj and call that Sj hat in this way. For each gene I, they divide Kij by the geometric mean of Kij across sample J. So probably I'll just write this as, so I'll just say sample J go from 1 to M samples in total, okay? And so the J, I'll just call that J prime from 1 to M. I multiply Kij prime across all samples. For this product, then I take the root, mth root. So this is what we call the geometric mean of gene I across samples. So they do this ratio, and you see this ratio is for gene I in sample J. So for each gene I, you can calculate this ratio. And then they take the median across all genes, across all gene I, and call that the estimated size, sample size effect, sample size factor, Sj. So starting from here, they will consider Sj to be this Sj hat. That's what the authors did. So I can sort of understand the rationale behind it as that when we want to pull things together as an average, median is more robust than the mean because it's less affected by outliers, extremely large values or small values. And the reason they want to do the geometric mean, so I think it's probably because they think here the counts are so I think probably they think the counts are multiplicated instead of additive. But I'm not sure. So this is something they didn't say, but this is just my guess. That is, if you think about this count, because many people work with log counts in this field. So, you know, in addition to this commonly used Poisson and NB distribution for counts, many people would take log transformed count. They may add 1 to avoid the log 0 issue. Log transformed count plus 1 and model that data using a normal distribution. So if you think from that perspective, then you take the log, then this geometric mean will become the arithmetic mean, and then you have the log counts. But these are just all my guesses. So you can open up your class, so you can offer your comments about how this makes sense. Okay, and given this Sj hat, we need to estimate other parameters, essentially Q and mu, right? These two things. This Rij, we don't need to worry about that because it's an intermediate variable. It's only here. We are only concerning these two parameters. Okay, so what did they do? You see, this is essentially the mean of the negative binomial, right? And it's about gene I. So it's reasonable that we take the samples for each condition. So for condition 0, we take all the samples under that condition to estimate Qi0. And we take all the samples under condition 1 to estimate Qi1. And we need to adjust for the size factor. So you can see essentially what they did is that they estimate Qi0, called the estimator hat, as the average of, okay, so I'll call M0 as the number of samples under condition 0. Okay, so M0 is defined as the summation of J from 1 to M. I'll use the indicator so that row J is 0. Okay, when it's 0, I get a 1 and I take the summation. And M1 is the summation J from 1 to M. Indicator rho j equals 1. So the number of samples in condition 0 and condition 1. So they did the average of the condition 0 samples and as the Kij. And here is for the j such that rho j equals 0 for those j. And they divide Kij by Sj hat. So in other words, what they try to do is that they consider Kij divided by Sj hat as the Rij. And then they take the average of the Rij's to estimate Qi0. So intuitively, that's the procedure, what they did. But you can actually justify this by saying, okay, if I take the expectation, so coming back here. So going down from this route, right? Think about what did I tell you? The tower rule. So if you look at that expectation of Kij, applying what we said, can be written as expectation of Kij given Rij, right? The tower rule is this. And then for the inner one, it's based on Poisson. We know its expectation of Sj, Rij. And because Sj is a constant, it gets out. And expectation of Rij is Qi rho j. So we get Sj, Qi rho j. Okay, so seeing that, then you would have the expectation of Kij equals this. So then to estimate this Qi rho j, you would divide Sj into the Kij. That's what they did here. But the thing is that they are ignoring Sj hat is what we estimated. They're treating this Sj hat as Sj, as the known Sj. Okay, that's the approximation they make here. And similarly, they do that for condition 1. So Qi1 hat, the estimate is 1 over M1. Summation for j such that rho j equals 1. And Kij over Sj hat, the same thing. It's for different group of samples. Okay, the estimated mean as this. And the next thing we need to estimate is the rho, right? That thing. And that's a little complicated here because for the variance, we know that if we do not have many samples, that's usually the case. For example, if you have only 3 samples under each condition, your M is only equal to 6. And then we have 3 points, three samples for each condition to estimate mu I0, another 3 samples to estimate mu I1. And we know this is not stable, right? If you recall, we talked about that empirical based approach for estimating the variance in the 2-sample t-test. That's exactly for this issue. We do not have a good stable estimate for the variance. So therefore, the authors also tried to address this issue. So what they did is something like 2-step. They first find some estimates for the mu, and then they plot the estimates of mu I0 and mu I1 against the Qi0 and Qi1. So they plot these estimates against one another. And they want to assume that there is some smooth relationship between the variance estimates and the mean estimate, and use that relationship as a smooth line to constrain their variance. Okay, so I'm going to give that 2-step introduction next. So to estimate this mu, the authors again use the tower rule I introduced. So basically, what they did is this. So what they did is that they wanted to estimate the variance. And for the variance estimation, we first use the sample variance we're familiar with. So about the estimation of mu I0 and mu I1. So the first step is that they propose something intermediate. They call that omega hat I0. And this is the naive estimator we can think of. It's 1 over M0 minus 1. And the summation is still over the samples so that their condition is 0. And for each sample, I take its scaled count, Kij divided by Sj hat, minus the mean. And the mean is what we computed here as Qi0 hat squared. This is the sample variance formula we are familiar with. And similarly, we will have omega I1, I'll just write it down, and 1 minus 1 rho j equals 1. Kij over Sj hat minus Q hat I1 squared. Okay, I have these two things. And then they want to say, are these two things good estimator for mu, right? So what they do is that they take expectation for each one. And so basically, because of this term here involved, so I'm going to skip the detail over there, but essentially, the authors show that they need to do some bias adjustment, which means that when they do omega I0 expectation. So for those of you who have listened to pay attention to the randomness I said in the beginning, we need to be clear when we say expectation, which are the random variables. Clearly here, Kij, the count is random, right, the Kij. And actually, this Q hat I0 is also random. And also, Sj hat is actually random as well. But we know the authors already treat this as constant already. So let's follow that and treat this as a constant. But still, we will be able to see that this, by treating this as a constant, is not just enough. Basically, we can show that this expectation is equal to mu I0 plus a term. And the term is actually coming out, I would say it should be Qi0, the true parameter, divided by M0 plus the summation across the samples in condition 0 over Sj. So this is the bias term, right? Once we get everything out, they should not be random. Everything should be a constant. So, but still, how do we adjust this bias? So what the authors proposed is that given we know this additional bias as this, so they propose to have an estimator just as called mu, which I should say mu I0 hat as this omega hat I0 minus this term. But for the term, because it involves some unknown parameters like Qi0 Sj, they just use the corresponding estimate. Qi0 hat over M0 1 over Sj hat. That's what they propose. And that's the estimator they, as the first step estimator. And similarly, they will have this mu I hat 1 for condition 1. So with this, then what they do is that they plotted everything here. So in the x-axis, you would have the either the Q hat I0 or Q hat I1, which are both put here. In the y-axis, you will have the nu hat I0 or nu hat I1, which are both here. So you will have every gene will give you 2 dots, okay? One corresponding to condition 0, one corresponding to condition 1. And you will plot all the genes for the 2 conditions right here. So that's it. So the number of dots is equals 2 times the number of genes. That's the number. And then what they did is that we know the estimate of the variance is unstable. So we try to fit a smooth line through this pattern. And then we try to adjust the variances, the variance estimates by shrinking every dot to the line. So in other words, we are going to adjust the estimates based on this line. So if I call this line F, if I call this line F hat, so essentially the final estimates to be used will be something called, okay, probably I can just call that the final estimates, I will call that, let's say, nu hat I0 star would be based on this fitted line. It's actually F hat at Q hat I0. Putting this number into it, get the value in the line. And nu hat I1 star is called F hat Q I1. And this is a common approach in statistics called shrinkage, or you can also call this as sort of empirical bias. The reason why we can say that is we are pulling all genes together to refine each gene's estimate. The curve here is fitted for all genes, not just for a single gene, but the estimate we want is to get one gene. So in other words, we are borrowing information from other genes to refine the estimate of gene I. And clearly there's always trade-off, bad pros and cons for this approach. So the pros is that you can make the estimates for the variances with smaller variances with this constraint. But the con is that you will have some bias introduced by this shrinkage, right? Because your estimation is not purely from data, but also from your assumption of the smooth pattern. Okay, so let's stop here. So now we have seen this DESeq framework. We introduced this in great detail about how the model is and how the authors did the parameter estimation. Then the next question is that we're going to use those estimates to answer this question. How do we perform hypothesis testing to test whether QI0 equals QI1? Okay, so we'll continue from there on next Tuesday. So please know that your first homework will be due on Friday, and we're going to assign the second homework Friday, which will be due in another 2 weeks. And you only have 3 homeworks for this quarter because you're going to work on the final project. So if you haven't found your partner yet, please start early. And also the data has already been released. Okay, if you want to stay in the Zoom, please feel free to do so. Otherwise, please feel free to leave. Bye.
Thank you.